record, share the screen, check out this video. I think you'll get a kick out of it.
Glad you don't have scurvy. In 1747, the first medical trial ever performed, Scottish physician James Lind found out that eating citrus fruits could cure scurvy. Now, today we know this works because citrus contains high levels of vitamin C. In fact, ascorbic acid, a common name for vitamin C, comes from the Latin for not scurvy. By issuing rations of lemon juice to sailors, the British Navy was able to pretty much eliminate the disease until the late 1800s, when polar explorers suddenly began to see scurvy again. The copper pots holding their lime juice had destroyed the vitamin C, but they were pretty confused. So despite James Lind's experiments 150 years before, citrus fruits became the enemy. And when Robert Falcon Scott set out to reach the South Pole in 1911, he carried the finest in canned meat products, biscuits, chocolate, tea, and zero vitamin C. A Norwegian team beat them to the pole by 5 weeks, and during their sad journey home, Scott and his team perished in a blizzard, sick and weak from what was probably scurvy. It had been so long since anyone had seen this disease, the British had forgotten how to prevent it. When we create such effective solutions, we can forget how serious the problems were. Thankfully, people today don't die of scurvy or polio. Since the introduction of Jonas Salk's polio vaccine in 1955, the disease has been nearly eradicated from the earth.
The thing to remember is that this is a continuous process.
Compare the 358 infections reported in 2014 to the 1940s, when 500,000 people per year were paralyzed or died from polio infections. Vaccines work. Our immune system is on constant alert against germy baddies with millions of white blood cells, each on the lookout for specific infections. When an immune cell meets its target, it replicates itself, and this clone army sends a barrage of protein weapons called antibodies to label the trash for cleanup. After the infection is gone, so-called memory cells stick around, ready to mount a fast attack in case this germ shows up again. This is how we develop immunity, and it works pretty well, since we're all still alive. But even with all that, some super bad germs can take us out before our immune sentries have had time to call up their clone army. This is especially true for young children. Their immune systems are fresh out of basic training. Thankfully, we have vaccines, which are made of tiny pieces or weakened versions of viruses or bacteria. They let our immune system see what the bad guys look like and recruit those all-important memory cells before we ever have to actually see the real enemy. Thanks to vaccines, the U.S. was able to eliminate measles in the year 2000.
Okay, get ready for some data. Give me a thumbs up if you can hear this video. Okay, cool, perfect. Because it's as loud as I can get it, so we'd kind of be stuck if we couldn't. Okay, get ready for some data, because this data comes quick. At the start of 1994, pretty much everybody was getting measles vaccines. We were able to get measles completely eliminated by the year 2000, which was pretty cool. It was gone from the United States.
Years, as more and more parents are refusing to vaccinate their children or are vaccinating them later than what doctors recommend, it's back. In most states, more than 90% of children are vaccinated, but that's not enough to keep a disease like measles at bay. In our episode about Ebola, we talked about a number called R0, the basic reproduction number for a disease, or the number of people infected by one person in a susceptible population. For Ebola, that number is low, but for measles, each sick person will infect up to 18 others. Luckily, vaccines can change that.
So R0's kind of an interesting issue because it has a lot to do with what's going on right now. The R0 is how many people will one sick person infect. And so if somebody came to class with Ebola, which is super dangerous, it's not that contagious. So that one sick person would make 2 other people sick with Ebola on average. But if somebody came to class with measles, they would make the entire class sick because it's so contagious, which is neat because our data is super shaky with coronavirus, but basically, right now what coronavirus is showing us is that like the mortality rate, as far as like what are my odds of kicking the bucket, is pretty low, but it's R0 seems to be really high. Like it's spreading quickly. You've probably seen exponential growth charts. Like here's when New York will hit its peak. Here's when South Dakota will hit its peak, and people are like graphing this out. And the R naught for Corona seems to be pretty high because it's spreading across the nation quickly. And so that just lets you know how many people you'll infect per person. And I think the tricky thing with coronavirus right now is they're finding this virus viable in people's breath 4 days before they have a fever or cough. Does that kind of make sense? Yeah.
Mhm.
Okay, cool. Aubrey, I see your hand. What's up?
So can you get corona, like can you get over it and then get it again and then spread it to more people?
Ooh, that's such a good question. I don't think I've read anything where we have data yet that I could confidently give you a yes, but we know that countries are getting like a second wave of it. I think, which this is a guess, okay, but if you had it and you built up the antibodies against it, and then 2 months later somebody else coughs it on you, I would say you either won't get it or you will get it for a seriously reduced time
Okay.
because you've got the immune system to fight it off, if that kind of makes sense.
Mhm.
Yeah, that's a great question. Any other questions about R naught? No? Okay, cool. We'll go back to the video.
The fraction of people who are vaccinated or immune can lower the reproduction number below 1, which means the disease is disappearing.
Hopefully that makes sense. If every person sick infects less than one other person, the disease is running out of hosts and will eventually go extinct. Oops, I got a comment box. Hold on, let me grab the chat box here. The frames. The video looks like the TES Oblivion dialogue animations. I'm sorry, Doug. I don't know what that means, but super neat. Sorry you don't have sound, Rhiannon. I apologize. I wish there was something I could do about that.
90% of unprotected people who come in contact with somebody who has measles, even just breathing the same air, will become infected. To control a super contagious virus like that, the vaccination rate has to be 95% or above. And right now, the US is lagging behind, and measles is making a comeback. The Guardian put together a simulation of just how this so-called herd immunity works. When enough of a population is vaccinated, even if it's not 100%, the herd can protect the unprotected. With vaccine refusal on the rise, our herd immunity is breaking down. Preventable diseases like measles.
Okay, get ready for the graphs. This stuff gets crazy. Pertussis is whooping cough.
Start drinking it right now.
These are your cases at 6,500 in 1950. We get that down to like the hundreds in the 80s, which is awesome. And then people stop vaccinating for a variety of reasons, and pertussis makes a comeback. And you're going to see this graph is almost the same for all of these diseases.
And whooping cough have become our scurvy. Most of us don't know anyone with measles. Not that bad, right? Yes, it is that bad. Before the age of vaccines, millions of people were killed by diseases that today are just bad memories. Vaccines have...
See this? Measles, estimated annual U.S. death rates before vaccine, 530,000 people every single year. Percent decrease since vaccines, 99%. That's insane. Like insane. 530,000 people died a year. Now it's 60, right? Like that percent decrease it's ridiculous. Like you don't get data that good. It's amazing.
Let us develop a sort of generational amnesia. Today we expect our children to grow up healthy, and we're lucky that we don't appreciate just how dangerous these diseases are. Like science writer Seth Mnookin says, vaccines are victims of their own success because of stories like Wakefield's discredited study wrongly linking vaccines and autism, and the news media's obsession with pictures of crying, terrified children being poked with needles. People are nervous about vaccines. This anxiety isn't new, though. When Edward Jenner in 1798 saw that milkmaids didn't catch smallpox, he realized that because they'd been exposed to the similar cowpox disease, they were immune. And based on this, he developed an early smallpox vaccine by inoculating humans with the cow virus. In fact, the word vaccine itself has bovine origins. Still, as far back as 1802, critics were claiming that the smallpox inoculation would turn you into a cow. Vaccines don't come without risk. Nothing does. But on average, fewer than 1 in a million people will experience a dangerous reaction to common vaccines. car accidents, playing outside, even walking will injure more children. Vaccines are asking us to do something alternate, to make a choice to protect not only ourselves and our children, but also those around us. Author Eulabis says that vaccines are one of the most empathetic things that we can do. A system that's based on people voluntarily using their bodies to protect other vulnerable people. That's something I hope we don't forget. Now, I'm a doctor, but I'm not that kind of doctor. It's natural to have questions about vaccines, and you should have a conversation with your medical professional. They want the best for you and yours. I will give you one prescription, though, and that's to subscribe.
All right, so now's the part where he asks you to subscribe to his show. Funny being here in South Dakota, where the word herd immunity probably makes more sense to us than other places. Does anybody in here worked with cows at all? Give me a thumbs up. Aaron's worked with cows. Anybody else worked with cows? Just Aaron? Okay. Aaron, you're going to have to be the sole spokesperson for cows, and Wyatt is not here, so poor Wyatt. He's going to miss out on this. Did you subscribe, Mr. Stecker? No, I did not subscribe to PBS on YouTube. Does barbecue count? Yes, Doug, barbecue counts as working with cows. I love it. What a good question. Oh, that's too funny. Okay, so here's the dumb question. Okay, Aaron, you're the sole spokesperson for cows. When it comes time for vaccination, this is normally in the spring, about the same time as, brandings, castration, that kind of stuff. Do you vaccinate cattle? Yes or no?
Yes.
Yes. Okay.
We
When
do.
you vaccinate a herd, do you vaccinate all the cows, some of the cows, 99% of the cows, half the cows? What do you do?
The sick ones.
The sick ones? Okay. You might be thinking antibiotics. That's true. You might
Basically.
for the sick ones. Yeah. When you do vaccines in the spring, you'll vaccinate all your cows because it's called herd immunity. No, Carson, eating meat does not count as working with cows. Great question.
What?
I know. That's such a good guess. But basically the idea is this. You have a variety of viruses that can affect cattle. So you round all the cows up, you vaccinate all the cows, and the cows are going to be fine because they've all been vaccinated against these diseases. Now, let's say you missed one. For whatever reason, you missed one cow. You might still be okay because if you have a herd of 20 cows, one cow misses its vaccine, there's not another cow in the herd to make that cow sick. Does that kind of make sense? Like, if you come to Rapid City Christian and you don't have a chickenpox vaccine, but you're in a class where every other kid in the class has a chickenpox vaccine, then you're fine because there's no one to give you chickenpox. The herd is protecting the unvaccinated. That's called herd immunity. Does that kind of make sense?
Mm-hmm.
Thumbs up. Okay, I got it. As well, a verbal. Perfect. So the problem with the herd immunity idea is when too many people start thinking this way, they don't want their kids vaccinated. The herd will protect them. The herd immunity breaks down, and measles comes back, and whooping cough comes back, and all these diseases kind of come back. And that is the case. And I'm not saying you have to go online and Google this by any means, but do they vaccinate during branding from Carson? Oftentimes they do, Carson. Good question.
Okay.
Depends. Every operation does kind of their own thing, but generally speaking, yeah, you'll get vaccinated in the spring.
Okay.
Not people, cows. People get vaccinated when they're little kids. Anyways, so the idea is that basically the herd can protect you, protect the unvaccinated. Too many people start thinking that way. Herd immunity breaks down, and these diseases come back. And so that's vaccines. There was a discredited study done linking vaccines and autism. The author of this study actually came out and said the study was wrong, but he knew he'd make a lot of money publishing it. And unfortunately, he fueled a lot of fires where people were afraid to get vaccinated because they thought it would mess up their tiny little cute kid. And that fear is deep-seated in the community of Google and blogs and Facebook.
Worth the money.
Worth the money. The fear is very real there for sure. And that's a tough thing because bear in mind at the same time that vaccines were blowing up in the 50s and the 60s, we also did a lot better job with how should we say this, diagnosing autism as a spectrum and doing a better job of classifying these different tiers of autism and rating kids on there. And so as you see autism increasing, not because it's more common, but because we're better medical professionals than we were 60 years ago, autism goes like this and vaccines go like this. And for you guys being smart biology students, you'll all recognize that as a correlation versus causation logical fallacy, which is you look at the two lines and you're like, oh my gosh, the rate of autism went up and vaccines went up. Vaccines cause autism. No, they don't. That's ridiculous.
Isms.
Isms?
Tisms.
Tisms, thank you. Multiple autisms, thanks. But of course, that's not the case. It's that the ability to diagnose it has increased over time, and vaccine use has increased over time, and overall our population's exploding, so it's working out fine. But here's this is my favorite correlation versus causation logical fallacy comic for you to think about. It says another huge study found no evidence that cell phone causes cancer. What was the World Health Organization thinking? And the other guy says, I think they just got it backwards. Huh? Well, take a look. Total cancer incidence right here, cell phone users. Okay, so they're both increasing, they're correlating. And then he says at the end, you're not. There's so many problems with that. Well, just to be safe, until I see more data, I'm going to assume cancer causes cell phones, right? Come on, it's awesome, right? It's the perfect logical fallacy. It's correlation versus causation logical fallacy. So hopefully you're all tracking with that because it's pretty interesting. So how do we control these diseases? Viral disease control is a tricky thing. Vaccines are really the only way to do so. You have to get the vaccine before you get the disease. Viruses do mutate quickly. They're not great with taking good care of their DNA. So medications lose their effectiveness as the virus continues to mutate. This is what happens with influenza and the flu vaccine, and why people are so frustrated with the flu vaccine, and how is it that some years I get vaccinated. From Thomas Roeder, so autism causes vaccines. Oh my goodness, this guy, you got nailed it. This is going on YouTube, so we got to take it careful. Or the anti-vaxxers there's going to be so much hate mail coming my way. It's going to be real, but that's okay. That's fine. So there's two types of vaccines that you can get. The first one's called an inactivated vaccine. An inactivated vaccine is a vaccine where researchers will alter the virus so it can't replicate, okay? It can't make more baby viruses, but the body can still recognize those surface proteins, build those memory cells, make antibodies against it, and store information in your immune system. There's some advantages to inactivated vaccines. The big advantage to these guys is they don't have to be refrigerated, which is awesome because that means we can transport them across the country inexpensively and even to other countries inexpensively. So that's a huge advantage to these guys. But your immune response is going to be weaker with an inactivated vaccine. So you might have to get a booster, right? It's not like, well, I got one and now I'm good for the rest of my life. That might not necessarily be the case. You might have to get boosters every 4 or 5 years. I'm trying to think of which one. Tdap needs boosters. And I know this because I hadn't had a Tdap in 5 years, and my wife was pregnant with our third kid, and she said, if you don't get a Tdap, you don't get to hold your new baby, because if you kill this kid with pertussis, you're in huge trouble. And I was like, are you being serious? And she's like, yeah, I'm being serious. Go get your stupid vaccine. It costs $6. So I went and got the Tdap, and then I could hold my kid without fear of giving him pertussis. Cold vaccines hurt a lot. I don't think, Thomas Roeder, that there are cold vaccines. We don't vaccinate for the common cold because the common cold is a huge family of viruses, ironically, including coronavirus. But you might mean like the vaccine, like liquid itself is cold, like to the touch. I don't know. That's a good question. Maybe they do from the group chat there. Okay, so other type of vaccine that you can get is what's called a live attenuated, and this is the kind that you want. Yes, he says he gets vaccines that are cold from the fridge and they hurt. Okay, got it. Live attenuated. These guys are awesome. You're going to know it if you get a live attenuated because your immune system is going to have to work a little bit to take care of this one. And so it's made from viruses that can still replicate. They can actually make baby viruses, but they're not virulent. They're not going to make you sick and spread and take over your lungs or anything like that. But your immune system is going to have to work, and they're going to give you a stronger immune response that lasts longer. And that's a good thing. It's not fun, but you guys have probably had the experience where you go in for a vaccine, you get vaccinated, and the next day you have like a runny nose, maybe a low-grade fever, some stomach pains, whatever, for a day or two, and they're gone. That was your immune system beating that virus, essentially. We gave you little tiny doses of the virus, let you beat it, and you kept that immunity. And I've seen that in all my kids. We take them in, they're just little tiny guys, 3 months old. They vaccinate them in the thighs and they're crying, and then they come home and the next day they're boogery and it's low grade fever and a cough. And I'm like, yeah, I know you're kind of miserable today, but that's 6 diseases that could have killed you that you're now immune to. So suck it up. You'll be better in a day. And they're always better in a day. And it's like, good job. You did it. You know, what do you do? Some downsides to attenuated vaccines. Since the virus can replicate, we can't give these to immunocompromised people. Some folks are immunocompromised. Think about people who have, if they're on chemotherapy or their white blood cells are doing poorly from something like leukemia. What else could make you immunocompromised? I'm trying to think of other things that can make you immunocompromised. If you have those kinds of things, HIV, AIDS, absolutely. Yeah, that's a great one. Oh, somebody saw it down here. Thank you. HIV, AIDS, yeah. New babies born from an HIV positive mom, there's a lot of blood in the birthing process. Not necessarily are going to be HIV positive. The odds are actually kind of small. But let's say the kid contracts HIV in the birthing process, and then you were to vaccinate that kiddo. Their white blood cells might not be able to beat the vaccine. And so when you think about herd immunity, you're immunocompromised. That's your 1% who can't get the vaccine. So you pretty much need everybody else to be vaccinated to protect the immunocompromised, which is funny because that's what we're all doing by staying home, is protecting the immunocompromised and the elderly and the hospitals who have not enough ventilators rather. So that's an attenuated vaccine. All right, let's talk about antiviral drugs. Antibiotics work great for bacteria, but for viruses, you pretty much just treat the symptoms. They're hot, cool them down. They're dehydrated, plug an IV in them. They can't breathe, throw them on a respirator and wait it out. Your immune system must win. This is what has to happen. And there's not really a lot of options outside of that. So in the 1950s, we did discover some really cool chemicals called interferons. And interferons we found were a protein that a cell would make when that cell was under attack. It would make these proteins and send them to neighboring cells as a message that, hey, there's a bad guy in the neighborhood. You need to lock your doors. Don't let anybody in because there's some bad stuff going down. And the other cells wouldn't let the virus in. And that was one of the ways that people were helping their white blood cells get caught up. And so when researchers discovered this, they were like, this is awesome. This is the best thing ever. All we have to do is make interferons in the lab that's specific to whatever virus. Shoot the interferons into the person and they'll be immune to the virus. It'll be so cool. What we found was that they're super hard to make in the lab. They don't last that long. They're specific to the person and they just didn't work as intended. So sadly, interferons were not a road we were able to go down successfully. Does anybody have a watch or a phone with a time on it? I don't have the time on my screen. How are we doing on time?
25.
Okay, thank you so much.
24.
24? Not 25. Come on. Every minute counts when I have 30-minute class periods. All right, cool. So anyways, that's an interferon. Super cool idea. Very optimistic. And it didn't work. So darn it, you go to the next thing. Okay, what's the next thing? Retroviral drugs. Drug research for HIV AIDS is reasonably well funded. It's okay. And basically the idea is if somebody's got HIV AIDS for life, is there anything we can do to slow the spread of that virus from one white blood cell to another? And the answer is basically yes. What you can do is you have to find a chemical that will stop the enzyme reverse transcriptase. You saw this enzyme in the video we watched. It took the viral RNA, turned it into viral DNA. And if we can stop that from happening, we could stop the virus. And we have actually made those. They're reasonably effective. There's new HIV drugs even back to just a few years ago that are incredibly successful, and people with HIV/AIDS are living very long lives. The problem is that they are outrageously expensive, like impossible. No one can afford these things, essentially. They're still experimental. But that's how most technology starts, and then it becomes more affordable with time. So, that's the way. You do not have to memorize these names, nor do you have to spell them correctly on a test. So don't freak out reading azithromycin. I'm going to fail this test. Relax. You don't have to spell that, okay? Take it easy. Next thing, protease inhibitors. Protease inhibitors are an antiviral drug that stops us from making the proteins needed to make the viral capsid. So the virus still gets inside of you, it makes new viral DNA, but it can't assemble viral proteins, which are kind of cool. So if you can't assemble viral proteins, then the virus can't get anywhere, which is really, really awesome. Protease inhibitors aren't terribly cost-effective or effective, but those are some of the drugs that we've kind of tried to make to stop viruses. But viruses are very, very specific, so it's a tricky thing. So far, it's been treat the symptoms, let the person's immune system beat the virus on its own, and that's essentially where we're at. So, questions on retroviral drugs, antiviral drugs before we move on? Once going twice? 3 times sold? Okay, cool. Moving on. Maybe moving on. All right, viral diseases. This is kind of where I thought we'd get today, so it's not terribly surprising. Viral diseases. Be prepared to know these with like a matching type question where we'll go through and have you kind of match them up. But your viral diseases are HIV. Most people are familiar with HIV, human immunodeficiency virus. HIV causes AIDS, and it's transmitted through blood essentially, and it lives in the white blood cells. The white blood cells become infected, infect other white blood cells, and of course HIV/AIDS doesn't kill people, but it makes their immune system so weak because their white blood cells are all infected that they end up dying of things that they would normally fight off. And so that's what happens. You end up getting the cold or pneumonia or the flu, and you die from that because your immune system is so poor. It's not the actual HIV that's causing you to die. 75% of those infected currently live in Africa. This is some kind of old statistics. I don't know how that still looks today, but that's HIV as a virus. Chickenpox and shingles, we've already talked about chickenpox and shingles. They are the same virus. They're a herpes DNA virus. They're super contagious. Most of you guys are vaccinated for those, and so that's probably not going to be an issue for you, which is that's pretty cool. The common cold is a virus. It is the leading cause of illness globally, but it's kind of a trick because there's so many different viruses that can give you the common cold that we can't vaccinate for it effectively, cost effectively, or even like utility. Like it won't work because there's so many viruses. We don't really vaccinate for the common cold because the common cold doesn't kill people. It makes you sick, and you have a fever or a headache, and you're sick for a day or two, and then you're over it. And so you beat so many viruses every year that there's no point in really vaccinating for the common cold. But that is a virus. Another virus is what's called hepatitis. Infectious hepatitis is hepatitis A. And that is a virus that gets to you through contaminated food or drinking water, which is pretty gross because it follows a fecal-oral route. And so somebody, a cook, a chef, whatever, went to the bathroom, did not wash their hands, had microscopic particles of fecal material on their hands, made a salad, something that's not cooked over an open flame or heated up to kill the viruses, and then from the salad or the sushi or the whatever, the person gets hepatitis, which literally means the inflammation of the liver, and the person's liver gets inflamed, and that's a virus. So again, they have to kind of wait it out. That's not very good. Influenza is the flu. The flu is airborne droplets. Droplet precaution is different from airborne. Droplet means like when someone coughs, their spit has to hit you, okay, and be inhaled through your nose, your mouth, your eyes, that kind of stuff. And so that's droplet precautions. Airborne is someone coughs it in the air and it stays suspended in the air, and you come in and inhale it later. So the flu is droplet precaution stuff, and so sneezing on door handles and those kinds of things, that's an important thing to bear in mind. Can you post this to right away after the video? Yes, Tanner, I absolutely will. Thanks for asking. Okay, sorry, I'm reading the thread of comments as well. So that's influenza. Influenza is a frustrating thing because new strains are developing all the time. If 2 people cough or sneeze 2 different strains of flu into your nose at the same time, and they infect the same lung cell, then the new baby virus that's assembled in your lung cell will be brand new to science. It's frustrating, right? So it's hard to vaccinate for the flu because basically, the National Institute of Health, the CDC, whoever does this, has to look out at future projections and say, okay, what strains do you think are going to be the most common next year? And trying to tell the future, they'll make like a little vaccination cocktail of pieces of all these different strains, and then basically vaccinate people that way. And so that's the flu and influenza, and you guys are all familiar with that one. So I'm thinking we got to be close to 2:30. Am I right? Somebody who's got a watch on them?
Yeah.
Yes? Okay. So I want to open it up to questions. What questions do you have from what we talked about today or our plan for the week or anything like that? Don.
The thing you told us about where you said it didn't work very well as a flu vaccine, it was individual per person. Do we need to know that for a test?
Say your question one more time. I'm a little confused by how you worded it.
The part where you said that it wasn't effective and it was very cost effective, very spendy, and it was to the individual person.
For the common cold?
Yeah.
Yeah, it's a great question. No, you don't have to know that for a test. That's a little too specific. Test questions are going to be like, which of the following viruses causes AIDS, right? That kind of matching stuff. You don't have to know the specifics of cost effectiveness and how effective vaccines are, that kind of stuff. That's just bonus stuff. So, yeah. Any other questions? All right, let me take you
Test
through
is
what
on
we're going to
Monday,
do.
right?
I think we're going to have to push it back, guys. That's what I was just going to talk to you about. So let's see. We have 1, 2, how many more slides? 3, 4, 5 for emerging viruses. So let's do that. Let's go. Tomorrow's Thursday. We'll finish the notes and we'll do a verbal review. I'll just ask you guys questions